So welcome to all of you here to this historic roundtable session. My name is Jürgen Renn from the Max Planck Institute for the History of Science, and I'm one of the organizers of this, together with Don Salisbury, who is from Austin College, and Wolfgang Rindler here, and many others have contributed to this, Jean Eisenstedt, Dean Rickles, so it really has been an international effort to bring this together. And first of all, the thanks go to the participants here on the table who have volunteered, even under some of the difficult conditions about which we have heard, to join us here in Dallas and come to this historic roundtable. We have already heard some great talks from some of the participants here. And I can only start with a little excuse, because there are some of you here, even amongst us in the audience, we should be sitting here, but you see the table is limited, and there is clearly a time constraint that we have to face. Also, there has been some biased selection here, I have to admit, towards the relativity community in disfavor of the astrophysics community, which may seem strange, and I can only say two things to this effect. One is, it will become clearer, I think, during the discussion why we have made this selection, and we try to compensate for it because there is still an Einstein year coming up in 2015, the centenary of general relativity. We'll intend to celebrate it all over the world, certainly also in Berlin, and I make the pledge here that we will make up for some of the deficiencies of today when it comes to the Einstein year and when we celebrate the centenary of general relativity in Berlin in 2015. But now let's come to this event, to another important celebration, the Texas meeting of December 1963. According to the reminiscences of Engelbert Schucking, the decision to hold this monumental first Texas symposium on relativistic astrophysics was made at the poolside on a long weekend, accompanied by strong martinis, the aim being, and I quote, to break the spell of Dallas boredom. And of course, as a historian, one is used to critically examine one's sources. The historical sources are our experimental data. So on the face of it, this sounds hardly believable, given that Schucking, Alfred Schultz, and Ivor Robinson had only been in Dallas for a few months since the founding of the Southwest Graduate Center. There can, however, be no doubt that the symposium marked a turning point both in the history of general relativity and in the history of astrophysics. The hallmark of success of this meeting appears to have been the amazing conjunction of two fields meeting and merging exactly at the right moment in history: astrophysics and general relativity. How can this be explained? That's a historical question. How can we explain this conjunction? You're all happy that this happened and it has formed a new field, a new community, but for a historian the question is, how could it happen? Okay, we are under great conditions to examine this question. Clearly, obviously, the recent discovery of quasars marked a turning point for astrophysics. Gradually, people had realized that they were compact, high redshift objects with an enormous luminosity. The discovery came in the wake of the invention and improvement of radio astronomy, and that's a history all by itself. There's a recent, very nice book by Longair on the cosmic century that tells this story in great detail. I can only warmly recommend it to you. But there is clearly a history to these achievements of astrophysics. Now for general relativity. And you start to see some of the reasons when, confronting a selection of relativists. For general relativity, this seems to have meant the end of a long period of stagnation and the beginning of a revitalization as an empirically motivated field of research. Accordingly, going beyond Schucking's 3 men and a woman by a pool account, one of the standard accounts of this remarkable coincidence is what we might call the Sleeping Beauty account. The Sleeping Beauty being the theory of general relativity, and the prince being the quasars, demanding its hand in marriage. In more serious terms, this is the explanation forwarded by eminent historians of relativity, in particular by Jean Eisenstedt, who unfortunately couldn't be here today, and testimonies of eminent physicists, such as Bernard Schutz, who is here in the audience with us. A common piece of evidence for the dormant period of general relativity is Richard Feynman's famous reaction in a letter to his wife to the 1962 Warsaw, or more precisely Jablona relativity meeting. I quote, "Remind me not to come to any more gravity conferences." More sociologically minded historians prefer a different account, which may be called the sugar daddy account, attributing the central role in the revitalization of general relativity to both private and military funding, such as came together to fund the Chapel Hill Relativity Meeting of 1957, or support that came from the Office of Aerospace Research of the US Air Force in support of relativity research from the mid-1950s to the early 1970s. This in the historians community is presently much discussed under the heading of Cold War science, Cold War rationality, and relates not just to applied military research, but also to supporting research for legitimatory purposes. Here, our purpose is, as I said already, on this unique occasion, together with the historical actors themselves, to examine and revisit such historical accounts. Was the marriage between astrophysics and general relativity just due to a coincidence, waking up the sleeping beauty of general relativity from which had lain dormant for so many years, having nothing to dream of but the three classical tests, because that was the empirical evidence for all this long period, the three classical tests. But then, how come it was nevertheless so ready for marriage? How come it nevertheless could react so quickly to the discovery of quasars? Or was it just quickly pepped up by the sugar daddy offering lavish funding in a Cold War climate, looking for new opportunities to show the power of science on both sides of the Iron Curtain? In order to clarify such issues, we will structure this discussion by focusing on three periods. The period immediately after World War II, the period around the Texas meeting, and the period following it. But now I would first like to briefly introduce each of the participants and then invite each of them to make a brief initial statement, and then we will launch into a conversation about these issues. At a suitable time, we will pause for a 15-minute break. And after the break, we will also welcome comments and questions from the audience. Now let me proceed in alphabetical order. We aren't arranged in alphabetical order, so you have to identify the person you will later identify. So let me start with Professor James Anderson from the Stevens Institute of Technology in New Jersey. Professor Dieter Brill from the University of Maryland. Professor Cecile DeWitt from the University of Texas in Austin. Professor Joshua Goldberg from Syracuse University. Professor Roy Kerr from the University of Canterbury, New Zealand. Professor Charles Misner from the University of Maryland. Professor Ezra Ted Newman from the University of Pittsburgh. Sir Roger Penrose from Oxford University. Professor Wolfgang Rindler from the University of Texas here at Dallas. Professor Louis Witten from the University of Cincinnati. And now we will start with Professor Anderson, who will give us his first introductory statement. Jim?
Yes. So I think from a very early age I want to learn about general relativity. I read all kinds of popular...
Would you turn on the mic?
Sorry.
Yeah, get close to the
And then push the button to turn it on. Is that better? Yeah. Okay. So I want to learn about general relativity from a very early time in my life. There were all kinds of popular accounts in the newspapers after Einstein published his 1915 paper, and Eddington observed the bending of light and the 1919 eclipse expeditions, and it was a very exciting time to read about this, but I never quite understood the articles. When I was in high school, I managed to get a hold of a copy of Tolman's book on relativity, thermodynamics, and cosmology, and that really got me interested in cosmology, although the results, the cosmological measurements that he talked about were about as meager as you could imagine. So when I got my MS at the University of Chicago, I looked around for some places I could learn about relativity and cosmology. I found there wasn't a single college, university in the country that had a cosmology department. But I did find Peter Bergman at Syracuse University was working on the quantization of general relativity, which sparked my interest. And I went there and got my PhD and also met my beloved wife. One of the great pleasures of life was to meet her and marry her. After that, one of the things that happened during that period, Feynman came to give a talk. And I got to drive him to the airport, and he said, "What are you working on?" I said, "I'm going to quantize general relativity." He said, "No, what problem are you working on?" And I didn't quite understand. I didn't get it then, but it took a little while for it to sink in. So then fast forward was the 1957 Chapel Hill Conference, which was mainly theoretical relativity. And it wasn't until the 63 Texas 1 conference that I actually heard that there were things that relativity might actually play a role in the real world. And that rekindled my interest in it. And after that, I went home and I wrote my book on the principles of relativity physics. I've been working on it ever since. So in a way, the fact that the 63 meeting contained real physical questions that relativity might play a role in was instrumental in bringing me back from what I had been doing before to get back into relativity. Okay.
Thank you very much. And thank you. This is really wonderful because we want to have a discussion, so thank you for being so brief. Dieter, would you continue?
Okay. Well, if I tried to follow Jim in telling personal history with respect to relativity, it'd be very short because it's basically I had the good fortune to be admitted to Princeton University. I met John Wheeler, and the rest is history, as it were. Once you meet John Wheeler, it's very hard to resist his ideas. But I thought I'd mention something, not so much as a reminiscence, but more as something forgotten. From the first Texas Symposium, because I was looking through the introductory summary in the proceedings, in the volume of proceedings by Hongyi Chu, and there's a curious thing that he mentions about Wheeler's talk, that during his talk on gravitational collapse, he mentioned that, or he postulated a new massless boson, the delta ray. Now, I had never heard Wheeler talk about the delta ray, so that seemed rather strange. And first of all, what was it? I went, like everybody does, to the internet and Googled it, and I should have known that the first thing that comes up is that it's the name of a rock band. But then there's also a Wikipedia article about it. It turns out that delta rays are sort of secondary electrons after bombarding a metal with alpha particles. Well, that couldn't have been it. There's also something usually called a delta resonance, and that couldn't have been it because that's a capital delta, whereas Hongyi Chu has a little delta in here. So then I added Wheeler to the search, and yes, there is a paper by Wheeler where he mentions delta rays, and that was in 1949. It had to do with secondary electrons produced by muons. Muons was one of the things Wheeler worked on. Well, that couldn't have been it. So I remembered that I took notes of these conferences, and I went back to my notes, and I'm afraid I found that Wheeler did talk about that. It didn't make too much sense, but it had the idea that when you have gravitational collapse, one of the themes that he kept pointing out was that matter can get crushed out of existence by this gravitational collapse. And he never really specified very much exactly what this crushing consisted of. I think, at least at the time, he thought it was just like annihilation, that it really would be turned into radiation. But then the worry was that you don't want to violate the conservation of baryon number. And so he postulated that the difference in baryon and antibaryon, that number that should be conserved, somehow also gets emitted when this crushing goes on by some kind of a zero rest mass particle, which he called the delta ray. It turned out, from my notes again, that was discussed to some extent by Gold and Bryce DeWitt. Hoyle thought it was a fascinating idea and emphasized that at the universe's creation, when matter was created, presumably these things would also have an influence. But that was actually it. I looked whether I had any notes from anything before or after. Actually, much of the talk at the Texas symposium that Wheeler gave, he had already given previously at a Stevens meeting. At that time, we really had a meeting of relativists almost every month. Stevens meetings at the Space Institute in New York and what have you. And so at that Stevens meeting, he gave this table of things that collapse, which he cited to show that the collapse is really a common phenomenon, not something very special. He gave that same table, but he didn't follow up with delta rays. And also after the conference, I couldn't find any such reference. So it's still a puzzle to me. But I understand that there's actually a recording of everything that went on at the first Texas meeting. And so I intend to listen to what Wheeler said and see whether I can find out what was really going on then.
Thank you very much. This is Cecile. DeWitt.
Can you hear me? Can you hear me? Yeah. Okay. My professional life began on D-Day, June 6, 1944. Until then, I was a student coping with the war and the German occupation, but on the whole, leading a very carefree life. On D-Day, my house was bombed flat, and everybody in the house was killed. And I was the oldest surviving female in my family, so I felt responsible for my surviving family. In other words, to go from a student life to a responsible life. And so on October 1st, 1944, I accepted an offer of a sort of paid internship in Joliot's lab. Joliot was a superb experimentalist, but he had nothing to do, he had no use of theoretical physicists. He considered them as parasites. But we're now in October 44. The war is not over, but Paris is liberated. So Joliot begins to get letters from colleagues in the US, in the UK, and in Canada. But my job was to understand those letters and to prepare an answer for Joliot. part of my job was also to get material for his lectures. He was lecturing on the diffusion of slow neutrons. And my part was to bring him some material on which he could build up his lectures. Needless to say, I was totally unable to do it. I knew nothing. I mean, there was no teaching of quantum physics in France anywhere. So I kept bugging Joliot, saying, I've got to go somewhere where I can meet somebody. I wouldn't even know which book to get out. So at that time, Walter Heitler, was also wanting to reconnect with the colleagues he had not seen for all through the war. So he offered to Joliot to a postdoc. I wasn't a postdoc, I had only an undergraduate degree, but I guess Joliot gave me that chance. And I went to Dublin, where I stayed for 2 years. However, going to Dublin was not that easy because, as I say, we were still under war condition. And in particular, it needed an exit visa. And to get an exit visa, it needed an ordre de mission. And I still have it. But it's a very precious document, and I'll read you a few sentences from it. So I've made a copy of it, because I don't want to hurt the original. So I'm leaving a copy of it here if some people want to see it. Anyway, what's interesting about it is that it's red, white, and blue, and it requests all the authority, military and civilian, French and Allied, to help Cecile Moret, that was me, in the accomplishment of my mission. That ordre de mission had to go through the French embassy in London, and the secretaries involved, both in Joliot's lab and afterwards at the French embassy, were too scared to get a description, to go back to their boss and say, what is that mission? What do we do? What is she supposed to do? Well, believe me, I was supposed to learn the harmonic oscillator, but they didn't know that. So all these secretaries were scared to go back to their boss. L'ordre de mission, c'était pour aller voir Dirac, Born, Chadwick, Rosenbluth, and Born. And so all these people got letters from the French embassy asking them to report to me what they had done during the war. Well, I can't start telling you more about it because I would exceed my time. But anyway, I did end up to Dublin, and I should mention actually another document of that period. In a sense, that's interesting because that's what the people thought who were the great physicists. But I've also brought another document, not totally separate, because I did it while I was at Joliot's lab. Immediately after Hiroshima, I was asked to write a book on nuclear energy and to explain the bomb. The reason I was asked is that whereas in the US and the UK and Canada, that work was classified, I was in Joliot's lab, where it was not classified. And we knew just about everything, not the final detail of putting it together, but basically all the cross-section and critical mass, all that we knew. So I produced that book. That's one of the original, but I've made a copy of it. I was anxious that people would not equate nuclear energy with a bomb. So I talk about nuclear energy, explain what it is, and then the bomb comes only as a very last chapter. And I was told, but I have no way to check it, that it did contribute to people in France not to be too nervous about nuclear energy. And that's why we use nuclear energy a lot. So I don't know. But if you want to see it or see what it says, I've made a photocopy, because I'm not giving that. I've made a photocopy of it. And I've also brought, but there's no time to talk about it, the whole issue of secrecy and openness and so on. And there's a very interesting story of that period called the Philadelphia story that you can also look. And since I'm primarily show and tell, because I cannot scan, I cannot do PowerPoint, but I can do show and tell. And one of the things I brought for show and tell is that beautiful book by Dean Rickles, because we're all sorry he's not here, which is based on the Air Force report which was mentioned. So for people in history who wants to compare, I mean, they kind of go together, but so that's what I brought. Now, in 1947, I had my PhD d'horreur, un doctorat d'état, on meson production in nuclear collision. But in those days, the pi meson and the mu meson were considered the same particle. So we were constructing very intricate things to explain the very limited data we had on nuclear energy or on cosmic rays. Cosmic rays were a great resource for high energy. Now, when I spoke about high energy at that period, I'm talking about a few MeV. So my... Well, I guess I'm taking too long, so I'll conclude. So I had eventually 2 years in Dublin, 1 year in Copenhagen, 2 years in Princeton. And all along, I wanted to share with other people the wonderful opportunity I've had through all that period. And I had those opportunities because I was not limited by career goals. So that was great. So I was thinking of how I could share or make it possible for people to understand and learn new recent development. So I created a new institution precisely to give to interested parties a way to understand and learn recent development, but really technically, not just what you learn in a quick conference, but so I thought and it became known as the Les Houches School. And I think I'd better stop here.
Let me just add one word on the book that you showed. This is the Chapel Hill Proceedings.
Yes.
And you can actually freely download it in the internet because it has appeared in the Edition Open Access. Just look that up on the web. It's an enterprise that Bernard Schütz, myself, and a few others have created, and that allows for open access distribution of natural science books.
Okay, thank you.
So our next speaker will be Joshua Goldberg, please.
Seem to want to go on. There we go.
It was your other finger that put it.
Oh, I see. Yeah, oh, that wasn't pushing the wrong button. I began to think about this. I didn't know anything about physics as a young child, but when I took physics in high school, I realized that that was where I wanted to try to spend my life. And as an undergraduate at the University of Rochester, I took, at that time, it was important to pass a language examination when you went to graduate school. I had to pass an examination knowing 2 languages, and I passed them both in German and French. And for the German, my physics professor at the time took me into the library at the university and pulled down the 1905 Zeitschrift für Physik and told me to read the 3 important papers by Einstein at that time. And that was really quite a revelation, and it was quite an exciting experience for me. When I got to Syracuse to do graduate work, I didn't know what kind of graduate work I would be interested in, but this was 1947, and this was the year that Peter Bergman also came to Syracuse. And that was kind of a happy marriage for me. It set me off in a direction where I had already had some inkling of an interest that I didn't know that I would be able to follow. And it gave me an entry to what was a burgeoning new field. There was trying to remember, in preparing for the Battle of Agincourt, the King Henry says something about we are a cheerful band of fellows, or words to that effect. And I think that those of us working around Peter in the early years of bringing general relativity into the mainstream of physics, I think we also felt ourselves being kind of a happy band of fellows working together and teaching ourselves what we needed to know. Anyway, somehow I ended up working for the Air Force, as Jürgen mentioned earlier, and I was a sponsor of. I was not only doing research on my own while working for the Air Force. I never did find out why they were interested in gravitational work, other than the fact that I think that there was supposed to be some mysterious general who thought that anti-gravity was a useful device for airplanes. As part of my role of supporting research in general relativity, I am instrumental in having the publication of the booklet that Cecile showed you, and also was instrumental in seeing that there was a certain amount of travel from Europe to the United States, and from the United States to other meetings, GR meetings in France. I couldn't get the Air Force to fly us into Warsaw at that time, but they were very supportive of our research until the Mansfield Amendment in the 70s killed the research program within the Air Force. Nonetheless, I was very fortunate in being able to come back to Syracuse in academic life in 1963, as it so happens. And so in the fall of '63, I was also very fortunate to be here at the first Texas meeting, and shared in the excitement of the new developments that were taking place then. Sorry, I'm losing language, but anyway, you know what I'm talking about. My biggest memory, or I shouldn't say quite the biggest memory, but one of the major memories that I have of that meeting was the opening of the meeting by Engelbert Schucking. The meeting was organized by Engelbert, Alfred Schild, and Ivor Robinson, and Engelbert from Hamburg, Ivor from somewhere in England. Don't remember exactly what his hometown was, and Alfred from Turkey. And Wolfgang stands up big and strong, and he says, "We Texans welcome you to Texas." And those of you who've heard his accent this morning can appreciate how that sounded. So anyway, I think that events have worked out for me in a very fortunate way, and I've had a very rich life in physics and in general relativity.
Thank you, sir. It also gives me an occasion to thank you and many of the others here who have also contributed to the preservation of the memory of this event. Even long before this round table, many of you have written up recollections, have contributed to historical enterprise, and in the name of the community of the historians of science, I would like to thank you for that. And this also gives me occasion to give the word to Roy Kerr, who has already this morning contributed to history once again by telling the story of the discovery of the metrics, and I would like to invite him again to say a few words to us.
All right. I'm a New Zealander. I was always a New Zealander. I was nearly an American at one time, but then I went back to New Zealand. When I went to the University of Canterbury in Christchurch, New Zealand, just after World War II. Well, actually, it was 1951. I started in the third year maths, and then I had a lot of time to spend waiting to graduate. And at one point, I remember going into the library, which was pathetic. There was no money, there were no books on modern physics, nothing. And I was looking for something to read on modern physics. And all I could find was 2 books on ether theory that had been around since the 19th century. Now, I knew ether theory was dead. I wasn't that ignorant, but I wanted to read something. And they were quite interesting because they were classical mechanics, and there was, tubes of forces and stresses and strains and all these calculations. But I learnt one really useful thing out of these books, which I'd like to pass to everybody under the age of 30. Well, if you're older, it's all right too. And that is, if in those days, the standard theory was ether theory. Now, if you wanted to graduate and get anywhere in physics, you better believe in ether theory because that was the standard model. Well, as you know, what happened to the standard model? Actually, what I was surprised to learn recently was there were still well-known professors in the 20s who still believed in ether theory, so it didn't die quite as soon as I thought. Anyway, I did learn something out of this. After waiting around and playing billiards and other games for a few years, I got to have spent enough time at the university to be able to go off to Cambridge in England, where I was doing my PhD. Now, I was a maths student interested in physics. So I started off with the world's preeminent professor in algebra, probably, Philip Hall, and in group theory. Now, with my 19th century education, I actually didn't know any group theory. I knew about groups of girls hanging out and chasing boys, but that was about as far as it went. So anyway, I had to take some coursework, and eventually he gave me 3 problems to take home for a week and work on. And I solved 2 of them. One involved the axiom of choice from memory, but the third one I couldn't get anywhere with, And so I went back and tail between my legs, and he got on the board and covered it with all the stuff that didn't solve the problem, but it was really interesting. It was only later I discovered it was the great unsolved problem of algebra on whether groups with finite representation, finite order, etc., were finite, something like that. So I decided then, well, to hell with it, I better become a physicist. So, okay, I got Salam as a supervisor, but I didn't know any physics. So I started taking lectures on elementary particles. In those days, every other week along came the alpha particle, the beta particle, the gamma, the delta, the epsilon, rho, so on it went. I'm lousy at remembering things like that. So I had no idea how I was going to remember what the hell the properties of this one were and that one, because there was no basis, no theory behind it. It was a mystery. You know, they were. So anyway, I struggled through this stuff, took some lectures from Dirac and took some on differential geometry from Todd, I think it was, a very famous differential geometer. The thing about his lectures was, God, stay at home and read the book, because you did not want to listen to those lectures. Then I got interested in relativity. How did I get interested in relativity? John Moffat was at the university at the time doing a PhD. He was trying to get relativity and electromagnetism together. He was trying to come up with a unified field theory. And he had one in which he assumed that the metric G mu nu was complex, not Hermitian, just complex, but complex and symmetric. And he wanted to work out the equations of motion of the particles to see what the forces were. So we got some papers on Einstein, Infeld, Hoffman stuff, and we used the methods, which are now called post-Newtonian approximation, things like that, but they used to be called EIH. And we looked up and we calculated the forces. And lo and behold, the electromagnetic force came out. This is slow motion. Peter Bergman explained to me why this was going to happen, and it was well known. Things were looking good until I suddenly had this thought. Wait a moment. We started with the complex Einstein equations. We used the radiation gauge, but since G mu nu is complex, G mu nu comma nu equals 0, that's 8 real equations. You've got 4 coordinate transformations. Basically, it was short for equations. It was incomplete. So that died. But in the process of doing this, I got interested in the motion of particles, this EIH stuff. And I read the latest papers, and what I saw was that the original paper had flaws, but it was a very, very good paper from 1938 with Einstein in it. Then Infeld took over and tried to correct the flaws and pretty much made it worse in every iteration. The one thing that, as a physicist, you probably find hard to believe was that in those days, what they were proving, if they thought about it, was that if you have several bodies, regardless of what they're like, you have equations of momentum and mass, but you can forget the equations of angular momentum because it never came in. Now, clearly, you know, there must have been something like conservation of angular momentum in any system of particles. So that should have told them that whatever they thought about their proofs, they couldn't be correct. So that's what I got involved with that, and I looked to see whether you really could build a theory in this way by successive approximation. what I found there was that really what you were trying to do was take a field up to a certain approximation, improve it one order by adding on something, but that you couldn't satisfy the field equations and the gauge conditions in every order exactly. And furthermore, you didn't want to. It was a silly way to go about it. So it all worked out in the end, and angular momentum and conservation thereof came in. I also worked on fast approximation to do that. Anyway, Bergman comes to Syracuse, not to Syracuse, to wherever I was, Cambridge, wasn't I? Yeah. Thank you. I've got my help here. And he offers me a job at Syracuse, so I went and joined them at Syracuse. And I gave some lectures on what I'd done, which was total waste of time. At the end of it, Peter said that, but really, these days nobody was interested in this several particle business. They were only interested in quantization and the stuff being done at there at the time, which was using, this is what he told me, using Lagrangian methods instead of Hamiltonian. I had the last laugh there because I eventually showed that the approach that he was using could not work. And I explained to him, because I started to calculate all the commutators one day on a huge sheet of paper. I thought somebody had to actually do something here. So as soon as I started, I realised it was a tautology what he was doing, and that he was never going to get out of the circle, which was true, he never did. So then Josh Goldberg offered me a job over working for the Air Force on the gravity bomb. And so off I went there. And,
you weren't supposed to admit that.
Well, we did design it. All we did was you chop off the top of a mountain, take it over Moscow, and drop it. The Air Force could work out the details of the delivery system, but we had the gravity bomb. So what did the Texas meeting mean to me? Having been sort of driven out of the motion of particles, which actually was the most interesting thing that's been done in physics over the last 30 years, in my opinion, is the work on the two-body problem. I mean, that's a difficult problem, and I hope it succeeds. Anyway, finally, we end up in Dallas, and real physics is coming back. Astrophysics is appearing in, and it needs relativity. So since then, well, in the last decade or so, I go to astrophysics meetings to hear about the latest explosions in the universe. I always did like explosions. And very much enjoy it, and it's great to see the combinations. I believe that in the next 30 years, all the great developments in physics are going to come out of observations off the Earth. Well, that's enough for today. I've had my 2 minutes.
Thank you very much, Professor Charles Misner is the next.
Thank you. Get a microphone going here. Good. Thank you. Well, I gave some reminiscences in a talk here of work on gravity. I'll skip how I got there through Notre Dame and Princeton. And to go on first, one of the questions Jürgen was asking of why were the relativists ready to absorb observations and money? And I think a lot of that was John Wheeler. John Wheeler said some places that he didn't dare, he was interested in gravity, but didn't dare take a student on gravity because in the 1930s, because their future would be hopeless. And so he and he wouldn't do research without students. He loved to work with students. So he did other things. He developed a wonderful reputation, had great strength coming in out of World War II, and decided that he would then come back to gravity. And that was going strong when in 1955, I guess, I joined him to work with him. And in 56, in the spring, he was Lorentz professor in Leiden. Joe Weber was with him, trying to get ready to do gravitational wave experiments. I was there doing whatever I could in gravity, in general relativity. And for a brief period, John worked with Reggie on the Reggie-Wheeler techniques for doing perturbations of Schwarzschild. And there were many other things going on, including John working on nuclear physics. But I think as he then focused on the neutron stars and what's the end point of stellar evolution, he was working in particular to try to bring relativity into the mainstream. And so this was happening already certainly by 57 at the conference. He was consciously trying to bring relativity into the mainstream, and he had the wherewithal to do it because he was so highly respected, and he chose a problem that involved a lot of nuclear physics as well as gravity. So where he was respected and where he wanted to be were melded nicely there. Now, I want to, in reaction to what these 3 points that Jürgen asked for, what happens before, in addition to that, now let me go to the second term, what happens as this work is going on. And I think for a historian, they might want to look at the aspect of themes. Gerald Holton had written a whole book about themes, sort of, are you an atomist or a continuum person, which was a great contest back in the times of Newton. But recently, those are also come up. I think, as of now, a big contrast is the reductionists. Those who, like Hawking and Weinberg, say that the way to understand physics is to understand what everything is made of. And they hope to find the theory of everything by finding the constituents. If you know what the ultimate constituents, what I call the Uratom, since the ordinary atom, the word has lost its meaning because it's applied to something that's very complex. So we're searching for the Uratom, and with the hope that that will allow us to explain everything, because nothing will be exempt from the laws that govern that, and everything will be made out of that, whatever it is. Now, the contrasting viewpoint, pushed a lot by Philip Anderson, is the emergent viewpoint, which says there's a lot of knowledge to be obtained by going to large systems with the old laws and discovering their language is useless. So from that point of view, he is, of course, defending solid-state physics, which is not going to change as you learn more things about quarks, and has yet got value in itself. It certainly has commercial value and conceptual value. So he's been pushing that idea that there are times when the microscopic view, the reductionist, doesn't really work. You can get a little ways towards handling complex problems involving gases and things like that by knowing they're made out of atoms. But without hydrodynamics, you wouldn't be able to do a lot of problems. You need entirely new ideas like pressure, volume, density, temperature, all of those kind of things that don't exist for single atoms or smaller things. So there's that big contrast, and I think it played a role in whether, as you began understanding the Schwarzschild solution and later the Kerr, were you going to focus on the matter and what happens to it? Is there a singularity in there that's going to tell us something about microphysics? Or are you going to accept that there's a new object, the black hole, which exists independent of how it was formed, because it can be formed in many, many different ways? Once you've got them, what good are they in the universe? What are their properties? How does nature use them? And how does nature produce them? But the production process is immediately lost almost in all these cases. And you can focus on these, which people have done now in recent years, as an emergent concept coming not from building out of atoms that it was produced in, but out of a new way of looking at larger scale things. So Anderson's viewpoint that bigger is different, more is different. That was his byword. More is different. So when you, in this case, when you have more volume, when you've got something bigger, the new language is needed, and the new language has entirely new things that don't exist on the small level, and that's the black hole in this case. Now, as a second point, that one, the existing history can be viewed from this point of view of a competition between these two different themes, the reductionist and the emergent view. Another thing is the question of what's coming next. And I just toss out one possibility here, and that is in 1963, that was the beginning of understanding black holes as an energy source for all kinds of things going on and observed in the universe. But we may in the future want to also change our view of black holes, and not entirely regarding them as energy sources, but pointing to the question of why does there have to be a black hole in the center of every galaxy? Is that serving some terribly useful purpose? And I say yes, because in addition to being an energy source, a black hole is a fabulous entropy sink. If you want to live, you absorb energy, you are creating all kinds of entropy in the process. How do you get rid of it? Well, if there weren't the carbon dioxide blanket that's going to keep it in, you just throw out infrared photons, which carry lots of entropy off into the universe. And we might want to say they're all headed towards the de Sitter horizon in the future. But anyway, you get rid of entropy that way, but it's not nearly as efficient as black holes. So because black holes, you can dump immense amounts of entropy onto a black hole and it doesn't bother it at all. I mean, it's got so much already that anything you want to do is practically irrelevant. So galaxies can form and can have us and solar systems and all kinds of beautiful organized things that do not look like maximum entropy situations, because any unnecessary entropy is freely disposable. You just find a scheme to throw it down the black hole and be done with it. So that's, I think, a view that may be useful. It's been pointed out for its importance for cosmology in recent years by Fang and Freeman Dyson. Independently, they came up with this same idea that the fact that self-gravitating systems have negative specific heats, which makes them A, unstable, and B, inaccessible to the thermodynamic definition of entropy, because you compute entropies by comparing quasi-stationary routes from one configuration of a system to another. Well, self-gravitating systems do not have stationary states. If they're big enough, they undergo continuing collapse, as Oppenheimer says. You haven't got any stationary states, you're at a loss for defining entropy thermodynamically. You might be able to get at it for information theory, this, that, and the other way. That one's gone. And so the fact that you have this ability to find systems that don't get controlled by the laws of entropy, you see that big blobs of gas that look like they're on the verge of absolute thermodynamic equilibrium. If you just wait long enough and if they're big enough, some tiny little instability will show up, because the negative specific heat means this is not a stable situation. And then eventually they start evolving and you get galaxies, and if you want interesting things in the galaxies and they produce too much entropy, you throw it down the black hole and you're on your way, and we're having a wonderful universe because of that. So I think that viewpoint that black holes are wonderful entropy sinks might be some of the guides to what we're going to be doing post-2013. Thank you.
Thank you very much. You made some great historical remarks on which I would like to press you, but later on, and thank you also for this excursion to black hole ecology. So our next speaker will be Ted Newman.
I've been in general relativity for close to 60 years now, and I cannot tell you how pleasant it has been. It has been one of the most wonderful possible lives that I could have. The people that I have met, worked with, and interact with has been almost uniformly of the highest moral, emotional character, decent, hardworking people. In this 60 years, I was just thinking now, how many people out of that out of the people that I've known over all those years, how many of those people can I say that I generally did not like or generally did not care for? We had one person as a graduate student who was obnoxious and basically a thief of ideas. This was out of the whole group of all of us at Syracuse. I was a graduate student of Peter Bergman's. There was one student, and he disappeared. He got his PhD, and we've never heard from him since. I think that goes hand in hand almost. The people that I met as a graduate student included Josh, Jim, Ray Sachs. Well, there's Peter Bergman, who was the most wonderful person. You can imagine I was in love with Peter Bergman. Really, he imbued us all with a love for physics and decency and honesty above all. I went, after my PhD, I went on a sabbatical a few years later, and I went to Copenhagen. I met, in Copenhagen, I met Christian Møller, who was a wonderful person. And then I went on to Hamburg, where I met Jürgen Ehlers, I met Jordan, Ray Sachs was back there, Wolfgang Kunt. Again, a whole series of people. And then I went to London and I met Herman Bondi, which was one of the great experiences of my life to work and interact with Herman Bondi. And I had a short interaction with Roger. We shared an office for maybe a couple of weeks there. That was my first interactions with Roger. I went back a few years later to Germany, and I met one character who must be the most unpleasant character I've ever met in my entire life in relativity. He was the second person on my list. And I'm dead serious about this. He was so unpleasant that you just couldn't stay in the same room with him. He also disappeared. He committed suicide several years ago. All his things came back to haunt him, and he also disappeared. In '61, I took a sabbatical and I went back to Syracuse. This was a year for me, probably in some sense the most exciting year of my entire life. That's when I went back to Syracuse. Peter had organized this international group there. So Andre Troutman was there. I met Andre Troutman for the first time, really. Engelbert Schucking was there. Ray Sachs came back. Josh was there. Who else we had? Ivor Robinson was there. It was just a fabulous set of people. And what was remarkable about it is that we all worked, and there was no jealousy. There was no backbiting. Everybody told everybody else what they were working on. No one worried about, are you going to steal my idea? For a matter of fact, many of the ideas were published many, many years later, after we never knew even whose ideas frequently were being told about, described. It was a complete mishmash of people telling everybody what they were working on. It was a fabulous year, and that's when I interacted very strongly with Roger, and we wrote our paper on the spin coefficient formalism. Over the years, I've met only one or two other people that I have found slightly on the unpleasant side, but they're a small minority. The friends I made back in late 50s and early 60s, I've remained friends with over all these years. I consider Josh and Jim to be two of my best friends. I don't see Ray Sachs any longer. It was a sad thing that he dropped out of the field, but Ray Sachs was my roommate for years, so we were great friends together. I thought that I would just end with two little anecdotes about some of the people that I met over these years. In 1963, I traveled to the Warsaw meeting on a plane with Alfred Schild and another very, very well-known physicist, a very, very famous physicist. I'm just not going to mention his name. He was a very, very good guy. Alfred was a wonderful person. This other physicist was a wonderful person, really a good, good person. We stayed, all three of us, with among others, stayed at the Hotel Europa in Warsaw. It was, in those days, it was a hangout for many people coming from different Soviet bloc countries, especially prostitutes. On the street in front of the hotel, you were always accosted. You want Elsa tonight? Or one night, in the middle of the night, I get a phone call, and it turned out to be Elsa. Elsa said, I can't repeat it in German, but she was talking to me, "Wollen wir zu deiner Zimmer kommt?" And I had just been married shortly before that, so I had to very politely decline Elsa's invitation. The next morning, I had breakfast with Alfred Schild and this other physicist that I will not mention. And I told him this a very unusual episode that had happened to me during the night. And this other physicist said, if she calls you again tonight, give her my room number. A few years later, right after the Copenhagen meeting, I had a wife and two children, and we went hiking in the Norwegian mountains. We went from mountain hut to mountain hut for a week. My kids were, I don't know, 6 or 8 or 5 and 7 or something like that. We had a wonderful time. We climbed through the Norwegian glaciers. The last full day, my wife didn't come with me, nor did my daughter, but my son and I climbed the highest mountain there in Norway, Galdhøpiggen. We got to the top of the mountain, and there was a little old man selling coffee and sandwiches. I came up every morning. He did that every day. But I met a Canadian physicist there who I had known. He had been also at the Copenhagen meeting. We talked a few minutes on the top of the mountain, and we ate our peanut butter and jam sandwiches. And then we came down the mountain, and we went to the mountain hut for supper. My wife, my kids, and I sat at a table, and 2 Norwegians sat down at the same table with us. They spoke Norwegian throughout the entire meal. At the end of the meal, one of the Norwegians said to me in perfect English, are you a physicist? And I said, yes. How did you know? He said, I heard on top of the mountain, I heard you talking, that sounded like you were talking physics to that chap on the mountain. So I admitted I was a physicist, and I asked him what he did, and he said he was an astronomer. He was Norwegian, but he was an astronomer at the Hamburg Observatory. Then he asked me, what is my specialty? And I said, general relativity. And he said, oh, that's interesting. He said, you know that there's nobody in Norway that does general relativity. And I said, no, you're wrong. There's a guy named Refsdal who does relativity. And he screams out, that's me. I swear, that's absolutely true. And he stopped doing relativity. He was now doing astrophysics. So these are I've had so many wonderful episodes like this over a lifetime that I just really feel so terribly lucky over it. Thank you.
Roger Penrose, would you please?
Yes. I may say I'm getting very nervous about having to tell my life story in 2 minutes. But so I'll only say a few odd things. First of all, relativity. I was doing pure mathematics, actually, for my research in Cambridge, although I had been inspired, first of all, by radio talks by Fred Hoyle, and I visited Cambridge just a bit before that, and I was visiting my brother, and there was some little problem I had about galaxies disappearing off the edge and so on, which I couldn't quite make sense of. And so my brother said, well, I know somebody, I don't know much about cosmology, but there's somebody sitting over there who will be able to help you, I think. And so that was Dennis Sharma. And when I went to Cambridge, Dennis Sharma sort of decided I was somebody who should be interested in relativity, or should be made to be interested in relativity. I'm not sure which. Anyway, he, I think, wanted me to change my research subject into relativity, but I thought it was a bit too far along the line for that. But I did learn an awful lot of physics from Dennis, and it was a tremendous experience. He was always somebody full of enthusiasm, full of knowledge about what was going on, and I think I learned a good deal of what I presently know in physics from him. I also had the advantage that in my earlier years of research, I thought you could, waste your time doing all sorts of other things. And so I went to lectures on completely different subjects, one of them being the lecture course by Herman Bondi, which was a fantastic course, I remember. The other course was a course by Paul Dirac, which was also fantastic in a different way. I thought it was incredibly beautiful. Some of my colleagues there were not so impressed, but that's because they'd already read his book. And they said, it's just the same as the book. Well, that, for me, that was fantastic. So I hadn't read his book at the time. I also, curiously, was trying to learn about two-component spinors when I was there for various reasons connected with my pure mathematical work, because I couldn't understand how you could take a square root of a vector. And Dennis was trying to get me to read books which were completely incomprehensible. I remember the book by Corson on relativistic wave equations, which I could make no sense of at all. But fortunately, Dirac, he took a week off from his normal course when he was doing his second term, which was quantum field theory, and he did one on two-component spinors. So I learnt my two-component spinors from Dirac, which made it particularly clear. People think of Dirac as a four-component spinor person, but he really did understand the two-component ones. And he wrote the best equation on relativistic wave equations of arbitrary spin, which I thought made complete sense, and I wasn't so sure about some of the others. Anyway, that was my upbringing with regard to physics. And then I went to Princeton because I noticed Wheeler was doing all sorts of crazy things which interested me very much. And I went there on a NATO fellowship. And then I started learning about things about gravitational collapse and so on. I'm trying to get my history right here, but I keep thinking of things which happened at one time, and it's completely inconsistent. Things that I must have known at one time when I was somewhere, and evidently I didn't know it because I couldn't have known it when I was there, and so on. So I can't make sense of it. But in particular, one thing I'm not sure I can make sense of was I went to, when I started to learn about these amazing things that were maybe, I remember Wheeler talking about how maybe there were things out there in the universe where the thing was getting down to its Schwarzschild radius. I mean, one tends to think of the Schwarzschild radius as a ridiculously tiny thing in the middle of a star or something which just had no relevance whatsoever to anything. But here we were apparently seeing objects which had some relevance to the Schwarzschild radius. Now that was at the Les Ouches meeting on relativity groups and topology. And there's people, I'm not sure whether it was before or after the Texas conference. I think it must have been before, because that was the first time I heard of this stuff. And I remember Wheeler getting very excited about it. And it seemed very mysterious to me that there could be objects which had a radius of something comparable with the Schwarzschild radius. I should say, just incidentally, about a comment that was made earlier about the subject of relativity being dormant before the Texas meeting. I get a completely different impression. There was a lot going on. It wasn't astrophysics, that's all. There was a lot going on. In particular, there was the work, I think Bondi had a tremendous influence with his study of asymptotic, well, also Troutman and other people, but I remember particularly Bondi's work, where he actually showed that you could get a measure of the energy in radiation carried away from a gravitationally radiating system. And I think that was a landmark. Lots of us tried to understand it in one way or another. Ray Sachs generalized it. Bondi considered only the axisymmetric case, and very quickly Ray Sachs generalized this to the general case. There was a bit of confusion about how to get rid of incoming radiation. They didn't quite have this right. I think Bondi thought there was some influence from Infeld, I seem to remember, about bodies under free motion, under gravity, maybe wouldn't radiate. And Bondi seemed to think there were some solutions which were free motions under gravity. That's because they hadn't quite seen how to get rid of incoming gravitational radiation. But there were a few things which needed ironing out, but it was a tremendous advance that. Certainly understanding energy was a tremendous advance. I think one of the reasons in the early days of relativity people had trouble believing in it was it was hard to make sense of the conservation of energy. There wasn't really a sensible energy tensor. The whole problem was that energy is not a local thing. Gravitational energy is not local, and to understand energy you have to do something such as going out to infinity or have some other way of understanding the non-locality. Einstein had a way of doing it which was very unsatisfactory because he had to introduce these things called pseudotensors, which to me didn't make much sense. But the idea was correct that you needed a non-local concept, which only made sense when you integrated it all up. But I think the Bondi work was really what Bondi and then Sachs was the work that sort of had a tremendous influence on the progress of relativity, and this was quite a long time before the Texas meeting, and very influential, certainly on me and others who tried to understand TED, of course. Now, where have we got to? I got to Princeton, where I was learning about gravitational collapse and Oppenheimer and Schneider and all these people. And then the Les Houches meeting, which I have the impression was earlier than the Texas meeting, and then the Texas meeting. Well, there was a lot in my, a lot happened to me that was important during that period. I remember in particular in the drive back from, I think, San Antonio. This was after the terrible business of the Kennedy assassination, when we were trying to recover our senses. And I think we went down south. And coming back from San Antonio, I remember being driven by Mr. Oshvat, very sadly, I think today, that had died only a very short while ago. So that was a very sad thing. And it was in this drive from San Antonio, I remember thinking of the idea that launched twistor theory. Now, I'm not going to talk about twistor theory, but it was, to me, an important year for that reason, quite apart from the Texas meeting, which was a very big event for me. It was a big event because, I started to appreciate the importance of these gravitationally collapsing things, or whatever they were. And I remember Wheeler emphasizing very much this question of the singularities. And whether, I think this may have occurred after the Texas meeting when I can't quite remember whether it was before or after, but it was around about that time, when Wheeler was clearly worrying about the singularity problem. And the question that was being raised was whether the singularity was a feature of the exact symmetry and perhaps of the particular equations of state that one had to assume for the matter, and the Oppenheimer-Snyder solution where the black hole, you had this collapse to a black hole, and the state of matter was a very simplified dust, and the much greater simplification was that you had exact spherical symmetry. And with exact spherical symmetry, everything would therefore sort of be focused right into the middle, and so perhaps it's not surprising that you've got a singularity there, and it might well be a fortuitous feature of this exact focusing that you only get in this kind of situation. Whereas in a situation where you had irregularities, who knows what would happen. And there was at this time this work done by the Russians, Lifshitz and Klatnikov, using methods that I was not able to understand at all. There were sort of things using all sorts of power series and techniques which didn't appeal to me much. I thought it was much nicer to look at things geometrically, and stimulated by this problem of the singularities and by the work that had been done to show that you really apparently have objects which can collapse to within their Schwarzschild horizon, I started to develop ideas. Well, curiously enough, one of the inputs into this is something which I'd never written down. I'd started to think about how to look at problems in general relativity which were quite generic, not trying to solve the equations which usually required putting symmetry assumptions in and so on, but looking in very general ways. And I was very much influenced when I was in Cambridge, before going to Princeton, by the people who were there doing cosmology, Bondi on the one hand, Dennis Sharma, whom I mentioned, Tommy Gold and Fred Hoyle, who were then very much promoting the steady-state model. The steady-state model had certain appeal to it from a sort of philosophical point of view. You didn't have to worry about where the universe came from because it was always there. And although Bondi was one of the great promoters of this scheme, he did worry about it because he liked general relativity more. And there was this problem of having to accommodate the steady-state model and general relativity at the same time. I think he was getting a bit schizophrenic about it. Fred Hoyle was able to cope with this by modifying the equations of general relativity. I don't think Bondi was so keen on that. So I started to think, well, I could see that you couldn't have it with, you couldn't have the steady-state model and general relativity at the same time if you didn't have negative energies. But then I thought maybe you could get around this if there were irregularities in it. So if you had a steady-state model which was not completely symmetrical, but all sorts of kinks and bumps on it. And so I started to think about how you might address this question. And I came up with what convinced me as a proof that you couldn't get around it, and that there was a contradiction with general relativity if you had certain completeness statements, and most particularly positive energy. But I never published that because at that stage the steady-state model was beginning to go out of favor anyway. The cosmic micro, I can't remember when that was now. but it was not so. Perhaps it was encountering difficulties from galaxy counts and all sorts of things. But anyway, so I'd developed techniques which I'd used also by looking at another influence in all this was looking at infinity from the conformal point of view, which seemed to me a nice way to handle the asymptotics that you needed for proving the Bondi type theorems. And I remember wasting months on trying to, I had an article which I wanted to put in an appendix, a proof that you didn't need to assume the topology of an asymptotically flat space-time was it's basically a sphere times time. And I cooked up some argument in the appendix of a paper I was writing using these kind of causal techniques, which turned out to be exactly what was needed for proving a nice theorem that you always got singularities when gravitational collapse went past a certain point. And that was the theorem that caused a lot of problems. I seem to remember when the London conference on GRG occurred afterwards, when I remember Charlie Misner trying to explain to the Russians about this theorem, and they were, it was completely two cultures of completely opposites, and there was no communication, I think, as far as I can remember, taking place at all.
Yeah.
But,
on that, I should say that I learned later that I was being very impolite because the Russians came there, and if their work were treated as inappropriate or false, they might have lost their jobs and maybe their lives.
Yes, that was a bad possibility. Well, they didn't lose their jobs, did they? Well, perhaps, fortunately, Belinsky came along. He joined Lifshitz and Klatnikov, and I don't know whether it was Belinsky's influence, but they discovered a mistake in what they'd done, And then everything was happy and cheerful because they could realize that there were enough solutions to incorporate. They were looking for how much freedom was there in the singular solutions, was there enough freedom that it could be the general situation. And they'd made a mistake in not incorporating certain types of solution. Can't remember exactly what the mistake was, but this was the problem that they'd had with my singularity theorem, because it seemed to contradict what they'd done, which it did in fact. But when Belinsky got together with them and they sorted out this mistake, and using ideas, also some of Charlie Misner's ideas, I'm not quite sure what order things came in, they were able to accommodate the general singularity, at least in their approach, and all was made much more cheerful at that stage. I think that's more or less I want to say. Thank you very much.
Les Houches was in the summer of 1963, before the Texas movement.
It was. That's what I thought. Thank you. Yeah.
Our next speaker will be Professor Wolfgang Rindler, here from Paris.
Yes. I should have mentioned I shared a room. I was just going to say, yes, before I say anything else, I'd like to just clear up a misunderstanding. Our good team gave me the compliment of being the organizer of this conference, but I'm only half the organizer. There are two co-chairs, and one is my good friend and colleague, Mustafa Ishak, and we share the work fairly and squarely, and he deserves as much credit as anybody else. As regards my own experiences, I actually studied in Liverpool during the war, in Liverpool, England, and I became a student at the University of Liverpool in 1941. And in 1941, I had hoped to study physics. Liverpool was quite well known for their fine physics. For example, they had Chadwick and they had Rotblat and people like that. But by the time I got there, all these fine physicists had actually left to work for the war effort, all sorts of things like radar and of course also the bomb, things like that. And so there were no physicists left, and I had to take mathematics instead, which of course I also liked. But that was the end of physics at that point for me. However, in the mathematics department, I was incredibly fortunate in having a great differential geometer, A.G. Walker, who is in fact the Walker of Robertson Walker metric. And he instilled a great love of differential geometry in me, and I thought that's what I would work on afterwards. Eventually, I finished at Liverpool and started teaching at the Cass College in London, which was then part of the university, and kept doing essentially differential geometry. But they needed a person who would teach relativity. Now, I had never had a course in relativity. I'd actually never known very much about relativity, but somebody had to teach it. And from experience, I knew that if you teach something, you learn it also. And I was keen to learn it, so I volunteered to teach it. And I learned an awful lot in my first year, teaching special relativity and eventually general relativity. And it seemed a fairly straightforward transition to go from differential geometry to relativity. In fact, it's a great advantage if you know differential geometry and before you actually do relativity. Now, in those days in England, you didn't have to get a PhD to teach at the university, and I was fairly lazy, and I thought maybe I could do better things. However, for example, in those days in England, the really elegant thing was to get a BA from Cambridge or Oxford and then just go on to being an FRS Fellow of the Royal Society. So this is by far the most elegant thing you can put after your name. I wasn't exactly aiming for that, but anyway. So after a couple of years, also there was a series of university textbooks in mathematics in those days in England called University of Mathematical Texts, which was a wonderful series, had some very fine books in it, and my ambition had always been to contribute to that series. I may have been a bit premature in publishing a book on, I just learned special relativity, but I really loved it and thought I understood it well. So I published that book on special relativity. It's just called Special Relativity. It had one little consequence, I only mentioned it because it had one little consequence later, which I'll come back to. And in the course of teaching relativity, there was a student in my class, I'll always remember her name, I just call her Mrs. F. And she wasn't actually a very good student, but one day she came to me and said, I've decided to do a PhD, and I found myself a PhD supervisor, G.J. Whitrow, at Imperial College. So, but after a while, I just kept thinking about it, and I thought, well, if Mrs. F can do that, I probably should do that also. And I asked Dr. Whitrow whether he would accept me as a PhD student, and he was happy to do that. At first he set me to work on kinematic relativity. He was a student of Milne's, a very good mathematician, and Whitrow was a disciple of kinematic relativity, which actually had no future at all.
Just get a little bit closer to the mic.
Okay.
Turn it on.
It's not on? Oh, it's on. No. I'm sorry, I fiddled with it, I turned it off. I'm awfully sorry. Okay, so I don't have to get any closer. Yeah, so whilst I was still teaching full-time, I went to Dr. Whitrow, and he started me to work on kinematic relativity, which was supposed to be a rival theory to general relativity invented by Milne. And Whitrow was a disciple of that, and he set me to work on that. But I found it very boring, and I was a little bit frustrated, until one very lucky thing happened. Whitrow had looked at the steady state theory. He didn't like it, and he wrote a letter to the Observatory, which is one of the sort of newsletters of the Royal Astronomical Society. And in that letter, which was published in the Observatory, he wrote that the steady state theory can't possibly be right because it had that mass horizon, I think they called it in those days. Well, he published that, but he didn't reckon with the feistiness of Bondi, Gold, and Hoyle, and a couple of weeks later, 3 weeks later, they answered him. And I still remember what they said. They said, we're not very worried about Dr. Whitrow's puff. We don't know what hurricanes, we don't know what hurricanes our theory will eventually be exposed to, but we're not worried about Dr. Whitrow's puff. Now, that was so rude. And so Whitrow came to me and said, do something. So, that was an extraordinarily lucky thing, because I think, like every other PhD student, much of it depends on whether you get a good problem or not. And anyway, I had this great good luck to get this particular problem. And in those days, horizons were mentioned in the literature. Usually, very often called mass horizons. Some people clearly understood it, like Eddington had obviously more or less understood it without actually saying very much about it, and other people had totally misunderstood what was going on. So it was a fun thing to work on, And eventually I found that there were actually two types of horizon, sort of duals of each other. One was called one I called actually the event horizon, and the other one I called the particle horizon. The particle horizon gave rise to what's called the horizon problem. In those days, anyway, it was called the horizon problem. And the particle horizon has the effect that distant regions in the universe had no time to interact, and so it was hard to explain why the universe was never this uniform and homogeneous. Because how could two different regions come into equilibrium without ever having been in contact? And in some indirect way, this helped create that helped to create the actually to somewhat of my sorrow, it helped to create the inflationary theory, inflationary scenario, because one of the reasons inflation was invented was in fact to cure the horizon problem. Anyway, I got those sorted out, and I met Bondi that way also. It then became a lifelong friendship, because Bondi was the external examiner in my dissertation defense, and he liked that dissertation very much, and we stayed essentially friends ever since then. And as a result of that friendship, very soon afterwards I went to Cornell and taught at Cornell, and after a number of years, I had a sabbatical and decided to spend a sabbatical with Bondi, who was at King's College in those days, in London. And I had the singular good fortune of sharing an office with Roger, which was one of the which was one of the great things about that sabbatical year. Roger, I think maybe for the first time, taught a wonderful course on spinners. And it was so beautiful, and what he got out of them was so beautiful, and many results just dropped out that would, in tensor language, have been extraordinarily difficult to prove. And I really fell in love with that subject, and I said to Roger, you absolutely have to publish that as a book. And he said, well, I've never written a book. I don't really feel like it, but you've written a book, you write it. And so that started our work on the spinner books. Roger, I think very soon after that, took a copy of our first. I remember we mimeographed what we had. So we made a first sketch of that book, and spent nights in Hamburg. By that time, were you in Hamburg? I think you were in Hamburg because you stopped in Hamburg before going to Warsaw. And so we spent all night with these old mimeograph machines, and we made I don't know how many copies of that spinner book, and Roger took it to Warsaw, and people liked it very well. And so he said, well, we've got to really write that up. And so we thought we'd write it up in a couple of months or so, but it actually took a couple of decades to finish that. Yeah, something like that. Well, quite apart from the fact that I'd written a book before, I enjoyed the work enormously, and it's sort of it was fascinating for me to work with Roger, that whom I could really consider to be a genius. In writing this book, which is largely Roger's, strange things would happen. So there'd be a theorem. So he said, well, we better write down this theorem. And I said, I don't know that theorem. Where does it come from? He said, well, it doesn't come from anywhere. It's just got to be true. And that happened more than once. He knew it's got to be true, but at this point, he hadn't bothered to prove it. Possibly he had proved it in his mind with this wonderful calculus he had developed, which was called Penrose beetles, which instead of spinners, there were little things that had arms and legs and all sorts of things, and they connected. Two little squares or something would connect with arms and legs, and that was a spinner proof of something which he could actually do in his mind. So I said, well, I don't know proof, you go and do it. So we worked along those lines, and it was a terrific experience. It lasted far, far longer than either of us expected. I must say, like Ted Newman said, relativity led to a really wonderful life. I met some wonderful people that way. It was easier in those days because relativity was a much smaller subject, and so the people in it were sort of, there's a pre-selection, and I was happy to meet almost everybody at the table here, apart from making friends with other people like Bondi, wonderful people like Dennis Sharma, who was also great friends with Roger, Jürgen Ehlers, who probably influenced my career after that enormously, and unfortunately died at 80, which I consider far too young compared to some others. Roman Cecile, and so on. You meet wonderful people, and it's a wonderful life. Teaching and researching led to a really very fine life. I think Jeremy Bernstein somewhere said, physics and the fine life it leads to. Anyway, so as I said, I was working at Cornell, and one day I got, in 1963 actually, I got a phone call from Ivor Robinson. And I was just by the way, Wolfgang, how much do you earn at Cornell? And I said $8,000. That was in '63. And I was said, well, how do you like to earn double that, 16,000? I said, I'd like that. He said, well, come and join us in Dallas. I'm just starting a new group in Dallas, and it would be nice if you came. So we started that, Ivor started that group. It was a small group, only Ivor, myself, and in fact Pishta Ojwat, who very sadly passed away a couple of weeks ago. It seemed a small group, but that institute that was newly formed and to which Ivor invited me, it was called the Southwest Center for Advanced Studies. Though small, it had quite a lot of money. It was funded by the three founders of Texas Instruments, and they primed the pump there, as it were, or as they used to say, by putting in $5 million to start with, which in 1963 was quite a large amount of money, and the rest was supposed to come in from grants that we would get from various places. It always amazed me that we got grants from the Air Force and from the Navy. Why should they be interested in relativity? But those were good days. Then, unfortunately, this terrible thing happened, the Kennedy assassination. I myself believe that had a lot to do with the sort of general decline in prestige of science. Kennedy, just by his optimistic outlook and on everything, on the future, and his insistence on doing science, for example, just like sending a man to the moon, which really fertilized science in 1,000 ways, produced a sort of optimistic spirit, which with his death also gradually, certainly decreased in America. Science doesn't nearly have the prestige these days as it had then, and obviously my instinct that it was funny that the Navy should, or the Air Force should support us, in fact was right. There came the Mansfield Amendment, which said that they can only support projects that would produce results very quickly, within 2 years, and if you had a project that might take longer than that, probably almost all projects in general relativity take a lot longer than 2 years. And so those funds dried up, and I just meant before the funds dried up, as I said, it was a rather flush. It was a wealthy institute. And although we were a small group of just 3 people, it never really was a group of 3 people, because there was always enough money to invite people to come and stay with us. And some wonderful people came through, and so it was usually not a group of 3, but possibly a group of 5, or sometimes even 6. I think, Roger, you spent a year with us, or you visit for full length, I mean, more than just a couple of days. So, and other people stayed with us. Jürgen Renn, I think, stayed with us for a year once, and so in that way, it was a wonderful life, which then eventually, and also talking about the origin of the Texas meetings. It's true, and it is only true that at the time it was said we will do that just to alleviate the Texas boredom, but that's one of those things that these nice aphorisms that Ivor always used, sometimes just for the sake of the aphorism. I actually, Ivor has a terrific brain and wonderful language skills, and the worst thing was to serve on a university committee or SCAS committee with Ivor, because there was no such thing as a short meeting. As soon as Ivor was on the committee, he would talk forever.
Maybe that's a good point where I can interrupt. I'm sorry.
Well, and not even necessarily points that he wanted to support, just for the sake of a nice speech. And so in that sense, I think to alleviate the Texas boredom isn't quite right. The real reason for the Texas Symposium was that we felt ourselves to be a fine institute, and nevertheless nobody had ever heard of us. And so I think Schicking and Shield were at University of Texas Austin, and they suggested, nobody at our university has ever heard of your institute. You have to put it on a map somehow. How should we put it on a map? Well, we'll put it on the map by inventing a convention, inventing a symposium. So what should we sympose on? And it was fairly clear that there was a huge problem in relativity. Those were the quasars. Where did they get their energy from? And it was clear that general relativity would be involved in that, in the solution of that problem. And so they invented the term relativistic astrophysics, and so it was called the first Texas Symposium on relativistic astrophysics. Unfortunately, I had to miss this morning's account by Engelbert Schicking. I'm sure he gave much of the details of that. He actually sent me
Wolfgang, it's me. It's just the moderator. I'm sorry.
so sorry.
Because the time is passing quickly, and we still have one further speaker, and then we have more time for that.
I'm done.
Okay.
I'm done.
Okay. Thank you very much. So our last speaker in this round is Professor Louis Witten.
I made a quick estimate here. We are instructed to speak for 2 or 3 minutes each, which lasts 25 minutes. By my watch, it's 2 hours. I made a quick estimate that the speakers must have been traveling with 95% the speed of light. I will try to stick to 2 or 3 minutes. I'm also, however, going to tell you very little about my personal life. The first astrophysics symposium not only started this field of relativistic astrophysics, but it ended a chapter which is a sort of interesting small chapter in the history of relativity. I'm referring to the worldwide craze that lasted for about 10 years in the discovery of anti-gravity. And I bring that in because that impacted on my life quite considerably. In the middle 1950s, I found myself after a different, I should say, youth than one might expect, employed by the Martin Company, now the Lockheed Martin Company, which was mentioned by the dean earlier. I had a PhD in physics, which I got shortly after World War II at Hopkins. At that time, Hopkins was still building the best diffraction gratings in the world. And they were measuring more atomic energy levels than anybody else in the world. And there was only one theoretical physicist on the faculty, and he was doing statistical mechanics, which was the subject of my thesis. In the mid-1950s then, I found myself employed at the Martin Company with a rather weak PhD, I would say, at the age of about 35, with a few children that I was interested in raising. And there was a vice president of ideas. That was not his title, but his function was to bring the company into new eras. The company was building airplanes and building rockets. It ultimately built the Titan rocket, which was used for many space vehicle flights. And the vice president had the idea, which was to him a wonderful idea, to develop anti-gravity. Of course, when he tried the idea in public, you can imagine the greeting he received by the scientists. So he said to himself, "Those poor bastards, I'll show them." He was vice president of a big company with a lot of money behind them, and they made a lot of money in those days. And the overhead rate was perhaps 150 to 200% and for a contract, which was cost plus, they were allowed to use 10% of the cost of the contract to do research. So he had the bright idea he was going to start a fundamental research laboratory in which anti-gravity would be discovered. I was a new employee, but a PhD in physics, and I was assigned to the new laboratory to discover anti-gravity, and I was told that's my assignment. Well, I said, I'll start by studying general relativity. And I did. I started by studying general relativity all by myself, no teachers, no colleagues, just Peter Bergman's book, which was, in retrospect, it was a very good book to study for me at the time because I knew no differential geometry. It was not the book one would pick today, I think, but it was a good book then. And I was helped by the fact that at that time, Jim Anderson started the seminar program at Stevens. And that's where I learned relativity, between the book and Stevens. For example, when I was at Stevens, if I had heard Charles say that black holes were a good sink for entropy, I would go home and find out what he's talking about. And so I would learn about entropy and black holes, and that black holes were a good sink for entropy. And if I learned that Roger said that energy was not localized, I would go home and find out why energy wasn't localized, and so forth. And so I learned relativity, and eventually I think I got there. However, on the way, there were some strange incidents. I had to give a couple of lectures. The Astronautical Society, the American Astronautical Society, was just founded because astronauts were beginning to go up in space, and they asked me to give a talk on anti-gravity. So I gave a talk which was to an audience assembled about the size of this room, but there was no standing room left after the audience came in. And I told a little bit about space contraction and time dilation, and that had to do with the metric, and I was interested in curved space and so on and so forth. And then during the question period, they said, "What are you doing about anti-gravity?" And I said, "Well, I'm not against gravity." And I told him that there was no serious scientist in the world studying something that he would call anti-gravity. During the time after my talk, several people came to me and said, "You had a big audience today. If you come next year, you won't have 25 people." And I said to myself, good, that was my aim. The same thing happened in Seattle. I won't go through those things. The same thing happened in Seattle. But you would be amazed at the number of people who know science, who know the mistakes that Newton made and the mistakes that Einstein made, and they have it right. I would get a person like that at least once a week for many weeks. That happened. Some of them were very simple ideas. The simple ideas are always hard to combat. I'll give you an example in a moment. Some were very difficult and complicated ideas, and they were obviously wrong by the second law or the first law of thermodynamics. They were easy. But suppose somebody comes to you and says, I have a rock of bismuth that demonstrates anti-gravity. What do? There was a vice president of the Martin Company who brought that up. He said, I read about a guy in Indiana who says the rock of bismuth. I said, it's nonsense. He said, how do you know it's nonsense? I said, there's no rock of bismuth that's anti-gravity. He said, how do you know there's not an isotope of bismuth that shows anti-gravity? Well, how do you know? What do you say to that? You have to test every atom of bismuth in the world? I mean, it's impossible. Well, there were lots of incidents of that type. But the power of a vice president of a big company is so great that the reason, I will answer Josh's question, the reason there was a laboratory at Wright Field was to find out what we were doing and to help us do it. And I got a contract from Wright Field to do it, to do gravity, which I did very happily. Just as an aside, I'm essentially finished because it only lasts.
You're moving at 20% speed of light.
Okay, I'll go faster. Where was I? Anyway, the laboratory was started because of the propaganda generated by my vice president. And I want everybody who talks sort of blows his own horn a little bit. So I will say that in my last report to Wright-Patterson, which you probably don't have anymore, I made the study had to do with conformal transformations. I made the remark that if somebody travels with acceleration, he will see particles. You'll see that in the final report, which of course became a very, I didn't make the calculation of how many particles he would see, unfortunately, but nevertheless, I knew that he would see particles. Well, thank you very much. I will perhaps privately give you some more examples if you wish, but I am slowing down.
So thank you very much. Time has passed quickly. We have just 10 minutes left. We could take a break, but we won't take a break now. You understand that? I would like, in finishing up our presentations, briefly come back to the Texas meeting. Briefly come back to the Texas meeting, the 1963 Texas meeting, because it seems to me the character of this meeting was a rather special one, because we have heard about the many motivations that stood behind your preoccupations with general relativity. Many of you have taken a turn from other fields of physics into general relativity that had a lot to do with the groups that existed, with the Bergman group in Syracuse, with the Bondi group in England, with Wheeler as a personality, as a fascinating personality. And this was a force field that shaped your life's trajectories into the direction of general relativity. But still there were many motivations: anti-gravity, geons, quantum gravity with the Bergman school, steady-state cosmology. And there was one that has received surprisingly little emphasis, namely gravitational radiation. And that comes also with a name that I haven't heard in the presentation, namely Felix Pirani. Felix Pirani, and you can see that in the proceedings of the Chapel Hill Conference, was one of the earliest people who thought of gravitational radiation really as a physical phenomenon. And he had quite visual ideas. He also did calculations and made suggestions. And if I remember correctly, he also was the one who drew attention to Petrov's classification, and thus introduced or stimulated a lot of the mathematical work. So I can see already reactions. This is exactly what I wanted to see. So one question is, what was the role of gravitational radiation? Although it was far from, observational, from the observational reach, it's still, I think disproves very much this concern that general relativity had been dormant or just a mathematical exercise. It provided kind of a leitmotif for many of those researchers in addition to the other preoccupations. So that's one set of questions to which I would like to briefly have your reactions. And another set of questions concerns the transformative role of the Texas meeting, because it drew all of a sudden these diverse groups together to a common concern, very much dealing with the quasars, with the collapse issues. So when did the collapse issue, when did the Oppenheimer-Snyder work, when did the Hoyle-Fowler interpretation of quasars, when did that come into your respective attention? When did you actually realize that this might become an attractor, as it were, for further work in general relativity? So I see Jim Anderson. Michael, please.
There was a time in the 50s when it was a question of whether gravitational radiation existed or not. There was a paper that proved that there was no gravitation. The question was, did it carry away energy or bring it into the system? That was also at question. And it took a long time before people finally settled and understood that energy wasn't the principal feature of gravitational radiation, but what it did to the system, what it did a detector, or what it did to the system that was radiating. And Joe, oh God.
Weber?
No. I'm drawing. It's a senior moment. Finally showed that, in fact, experimentally, that gravitational radiation did exist in the sense that it took energy away from a system, and that was the first, and as far as I know, the only time that gravitational radiation has been observed, or rather the first time that gravitational radiation, the effect of it was observed, and it became a real thing and answered these questions about whether it existed or not.
I think Roger Penrose wanted to say something.
Well, I just wanted to reiterate a point I made before. I mean, the fact that energy was carried away by gravitational waves was basically made clear by Bondi in his work.
And wasn't he triggered by Felix Pirani insisting on this point?
Well, Felix Pirani was, I could easily have mentioned him. He certainly had a big influence on me, partly just because he understood the mathematics very well, and I learned a lot from him when I was learning relativity in Cambridge. but certainly the recognition that the curvature tensor was playing an important role, and the fact that it had an effect on orbits of particles and so on, as well as the classification. The classification thing was not, well, slightly, well, I wouldn't say it was exactly right, but I mean, it was certainly, to understand the connection with the Petrov stuff was of significance. I mean, it found its place in the work that was done by Bondi, and particularly Sachs, in realizing that Troutman also, I remember, the leading term was null, and then in more detail, the next term was type 3, and then so on. This peeling property, which was a very important understanding in what was happening in gravitational radiation. So these things were all very much connected with the fact that energy was carried away, and the nature of gravitational waves, and all this sort of thing.
Okay, thank you. Josh, you want to say something?
Lou said something about Tooting once more, and so I think, sorry. I want to go back with a little bit of history, and along with Lou, to do a little tooting. In the late 40s and 50s, Infeld and a student of his, Scheidegger, did some calculations using the EIH calculation and concluded that as a result, there was no gravitational radiation. And Scheidegger. Those of us who were at Syracuse at the time didn't believe the result. We believed that clearly first order GR had a wave equation, and if it had a wave equation, there ought to be gravitational radiation associated with that. But it was a first order. It did not take into account the nonlinear effects. I did an extensive, it was published in 1956, about the same time, roughly the same time as Felix Pirani published his analysis of or review of the Petrov classification. But this was an EIH calculation that showed that moving bodies, interacting gravitational bodies, would exhibit gravitational radiation. The problem with the Infeld-Scheidegger calculation is that at very low orders where they introduced the radiative effect, parts of the field, they had no effect on the Riemann tensor. They were simply coordinate transformations. They were not physical properties of space. I carried out the calculation to the 11th order in V over C, which today is known as the 3.5 post-Newtonian order. And at that point, it's quite clear that the Riemann tensor is not zero, and that gravitational radiation is being carried off. So, but I do want to emphasize the fact that it's not, having done the calculation is one thing, and you're talking about what people believed as well. I think for the most part, people believed that there was gravitational radiation. And I think that Infeld was an odd person out. But I also want to point out, in this case, that at the Chapel Hill Conference, which was in 1957, that Bondi and Gold left that conference not believing in the existence of gravitational radiation. And in a subsequent paper by Bondi, where he first exhibits a plane wave slab in Nature, he says that explicitly, that he believed, had up to that point, believed the Infeld-Scheidegger calculation.
Ted Newman was waiting.
Yeah.
Well, could I just, hey, 1 second, Joe Taylor please, just let me say, it was Joe Taylor that first observed. I've gotten over the senior moment too late. I said Joe, but I didn't say Taylor. Sorry.
It's unquestionably true that Bondi made an absolutely, as Roger's been saying, made absolutely a profound discovery, and his results have been unbelievably productive over the years. There's a historical question, though, that one of the Poles, Piotr Kruszczal, has been pushing for many years now. That I think it's worth. Really for understanding the full history. Kruszczal is saying that Troutman actually had the same results that Bondi had. I've actually gone and talked to Troutman about it. I've asked Troutman about it, and you cannot trust Troutman at all. The reason you cannot trust Troutman is that he is so bloody modest that he will not take credit for something, even if he has done it. So at the present time, Kruszczal is absolutely saying that Troutman had those results. When I talk about it, when I give a lecture, I always refer to it as the Bondi-Troutman energy momentum loss theorem. But I think it's an interesting historical question.
I think Roger Penrose will have the last word, and I will make a concluding remark so we can come in time to the dinner.
I was only going to make a small remark about trusting Troutman. He was prepared to accept credit for some things.
Yeah.
I remember the issue of understanding gauge theories in terms of fiber bundles. And he was saying, yes, he thought he was the first person.
Yes. Yeah.
So the fact that he denied, I think you have to give a little bit of weight to the fact that he was denying that he'd actually done it. So I think he probably didn't have as much as Bondi had.
I think you're right.
He had some understanding of it.
May I comment on that just for a moment? At that time...
Microphone.
Oh, sorry. It was on, but I wasn't speaking into it. I've lost my train of thought for a moment. Troutman, right. Troutman, before Bondi's results became public, Troutman created a formal analysis of what the gravitational radiation field should look like at null infinity. He had what was called an outgoing null radiation condition. And I think that was a very important contribution to the whole field at that time, because we didn't know exactly how to go about the calculation or how to trust the calculations that we were doing, because we were using at the time the so-called pseudotensor, Einstein's pseudotensor, for the calculations, and we know that has coordinate problems. It's not a tensor. It was a mathematical construct which came out of the theory.
Yes, I think Troutman had some understanding of the asymptote, the leading term we know.
He had that understanding.
But I think whether he actually had the formula for the radiation energy.
That's what I was a little bit fuzzy about it, because I don't know.
Right.
I thought that Troutman took the Einstein-Infeld-Hoffmann calculations up to a very high order, tracing the radiative path, and that he showed his radiation. Obviously, if you use half advanced plus half retarded, or instead of the retarded potential or the advanced potential, you're going to get completely different
Clearly,
results.
the work of André Troutman. Clearly, the work of André Troutman is a worthy historical subject
up to a high level. Is this on?
To explore. I would like to conclude with 3 brief remarks. The first is to thank you all. History is clearly a widely open field, and there would be much more room and space and time needed for discussing all the issues that you have brought up, and clearly they are connected not just to the past but to the future as well. You know, we have heard new visions here at the table, and for us historians, it was really a feast. It was a pleasure to have your comments, and I think it was also quite interesting for the audience who continue to work on many of the problems that you have brought up. The second remark I would like to make is it has also become quite clear from the discussions and presentations that general relativity in 1963 wasn't the unprepared dormant beauty that needed to be awakened by astrophysics. There was a lot going on, and without some of the magnificent theoretical and mathematical work that had preceded the turning point of 1963, general relativity wouldn't have been ready for the marriage with astrophysics. And that has, I think it's contributing to a new view of the development of general relativity. And the third and final remark really goes to the Texas Astrophysics meeting. I think, you know, the many networks of collaborations and friendships that you have been mentioning came to a culmination point at the Texas meeting. You know, you were all drawing on this enormous potential in the background to make this meeting a very special event. And I think the organizers had an incredible intuition tuning this meeting to the right kind of questions. It's one of the few physics meetings that were specifically dedicated to a theme, like the famous 1911 Solvay conference, focusing a lot of heterogeneous concerns onto the quantum problems, and thus preparing the ground for the emergence of quantum mechanics. And so was the Texas Symposium really a transformative, a catalytic event that brought groups together and created a community that is still live and well and operative today. So in that sense, I thank you all for giving us those insights, and we finish almost in time for the dinner. Thank you for the audience.